In this lecture, I'm going to show you an example of how to work with the binomial distributions. First, we have to be able to recognize the binomial setting. Bernoulli trials are worth you looking into. If you just do a Google search on those, it'll kind of set the stage for what we're looking at here. But with the binomial conditions, with the binomial setting, we have to have 4 conditions that are met. And the first is that I have to be able to organize my outcomes into 2 different categories, either success or failure. That doesn't mean you have exactly 2 outcomes. For example, there might be 5 ways to win at a certain game, and those 5 wins those 5 possibilities could constitute a success, while the other possibilities would constitute failure. I must have independent trials. The result of what happens in one trial cannot affect the probability of what happens on the next trial. So think of flipping a coin. When I flip a coin one time, there's a 50% chance that I'll get heads. If I flip it again and it's a fair coin, there's still a 50% chance that I'll get heads. Before beginning the trials, I have to know exactly how many I will complete, and then on each trial, the probability of success must be the same. So for example, if we're talking about the probability of guessing a question correct on a multiple choice test, and I have some questions that have 4 choices, some questions that have 5 choices, the probability of success changes from 0.25 to 0.2. So you have to make sure that the probability of success is the same. Next, as we talked about in class, I want you to be able to understand the mean and the standard deviation of a binomial random variable. There is a proof associated with this, and I can show you that if you're interested. Just see me in class one day and I can give you a copy of what that proof looks like. Remember that these formulas only work for binomial distributions. They don't work for anything else. So the mean of a binomial random variable is n times p, where n is the number of trials and p is the probability of success. The standard deviation is np 1 minus p, all square rooted. Okay, let's take a look at these 2 situations. Both we're choosing students in the school randomly to determine whether or not they are left-handed. And in each situation, we have exactly 10% of the students in the school being left-handed. So we want to determine whether or not these situations would represent binomial random settings. So we have those 4 conditions. We need to have binary outcomes. So can the outcomes that we're looking for be categorized as success or failure? I think here we would say yes. That when I choose a student, they're either going to be left-handed or right-handed. Next, we want to know whether or not the outcomes are independent. So we're talking about the characteristic of one student being left-handed, whether or not that's independent of another student's left-handedness. And I think it's safe to say here that this assumption is valid. Next, I want to know whether or not prior to choosing students, I know exactly how many students I'm going to choose. If we look here, it says we're going to select students at random, one at a time, until we find someone who is left-handed. That means it could take me 1 time, it could take me 20 times, it could take me 300 times. So for number of trials known, here we would have to say no. The idea that we're choosing until we find someone who is left-handed lets us know that we're not sure how many trials we will actually have to perform. And then lastly, is the probability of success the same from trial to trial? Well, we're looking at 10% of the students being left-handed. That's not going to change just because I'm choosing students at a time. So our probability of success is 10, or 0.10 for 10%, and this does not change. So in order for this situation to be binomial, we would need all 4 of these to be met. We've met it with binary outcomes. We've met it with independence of outcomes. We have not met the number of trials condition, although we have met the probability of success condition. So we would have to say that this is not a binomial setting. Now, if we look in this last one, we have the exact same situation with a minor change. The change is that we are going to select 15 students at random. W is the number of students who are left-handed. So we have everything represented above. meaning that we have the binary outcomes, we have independence of trials. This time, we know that we are choosing 15 students, and we know this before we start, and the probability of success does not change. So all of the ones that are checked, we could verify the conditions the same as we have above. Notice that I'm only writing this out at the bottom because we have previously stated how these are validated above. Please don't just write bins and place check marks. We know that we have to communicate statistics, so that will not work well in your favor if that's all you choose to do. So now how do we actually work with this? Now we want to be able to use the probability formula. So we have the situation that I left you with at the bottom of the last slide, and we want to find the probability that exactly 3 of the students in the sample are left-handed. So we want the probability that W equals 3. So what we know is that the binomial probability formula says that if I want to know the probability that a random variable x that follows a binomial distribution takes on a certain value k, then I look at the number of k combinations there are out of n trials. I multiply that by the probability of success raised to the number of successes, and then I multiply that by the probability of failure raised to the number of failures. So we have n choose k times p to the k times 1 minus p to the n minus k. So if we follow that pattern for W being 3, then we're looking at 15 choose 3. Probability of success is 0.1. I'm interested in 3 successes. Probability of failure is 0.9. And if there are 3 out of 15 that are successes, then that means that there are 12 out of 15 that are failures. If you work through this on your calculator, this is 15C3 times 0.1 to the third times 0.9 to the 12th. And when you multiply all that together, you should get 0.1285. So that means that there is about a 12.85% chance that exactly 3 students in the sample are left-handed. This next question asks if I'd be surprised to find that the random sample contained 4 or more left-handed students, and we're going to compute the probability that W is greater than or equal to 4 and use this result to support our answer. So first, let's deal with this idea of the probability that W is greater than or equal to 4. And this is 4 out of 15. Now, this translates to the probability that W equals 4, or W equals 5, or 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's a lot of times to use that binomial probability formula. I could change this so that it's 1 minus the probability that W is less than or equal to 3, which in a discrete distribution serves as the complement of the probability that we're actually trying to find. So if I can find that probability and subtract from 1, then I can find the values that I'm looking for. Now, to find this, I would need to know or really understand that this probability of W being less than or equal to 3 means that I have to use my probability formula for binomial distribution for the values of 0, 1, 2, and 3. And so this is one way to write that. We can say it's 1 minus, I can use a summation of k going from 0 to 3 in terms of the number of successes. We have 15 trials. We're choosing k at a time. P is 0.1, and we want that raised to whatever the power of k is. And then 0.9 is success or failure, and we want that raised to the power of whatever 15 minus k is. This is just a shorthand way of writing out these probabilities. Now, you will, or I would recommend rather, I'd say that you use your calculator to find these. This information is in your textbook, and I'll put on the next slide how you would find this information. But once I do this, then you're looking at a probability of 0.0556. So the question is, would I be surprised that the sample contained 4 or more? With a probability of 5%, I would be surprised, as that's rather low. It's not statistically significant, but it is a low practical probability of finding 4 or more students in the sample. This last slide shows you calculator commands in working with the binomial probabilities. You want to understand the difference between the PDF and the CDF. PDF is probability density function. It shows you the probability that X will equal a value. It's exactly that number of successes. CDF is cumulative. It begins counting at 0 up to the number that you provided. So it provides the probability that X will give you successes that are less than or equal to the number that you insert. And so it walks you through here what the components are. N is the number of successes. P is the probability of success. Sorry, go back. N is the number of trials. P is the probability of success. And K is the number of successes. If I were to write calculator commands for the example we just did with the number of left-handed people, then I would want, for probability that X equals 3, I would use this command, binom, PDF, N is 15, probability of success is 0.1, and I'm looking for 3. Now note, this is a calculator command. In no way does it suffice for work. In the next example, I was asked if I would be surprised if the probability, would I be surprised to find more than 4 in the sample, 4 or more in the sample. So this is the probability that X is greater than or equal to 4. Notice that CDF only gives me less than or equal to. In the example, I had you change this to 1 minus the probability that X is less than or equal to 3. And so then I can do 1 minus binomial CDF, where N is 15, number of trials is 0.1, and 3 is the number of the maximum number of successes that I'm looking for. These commands can be found under second and distribution on your menu. It might even say second variables, but look for the distribution in light blue or whatever the alternating color of your contrasting color of your calculator is. Try and use this to help you work through examples for the rest of the weekend, and when we get back in class on Monday, then we can talk about any questions that you have then. We also have some more to add to this that has to do with the normal approximation to the binomial, which is very useful for the remainder of the things that we're doing in the course. Have a good weekend, and I'll see you guys on Monday.